Okay, let's go through the contents of this video. First, I will explain what is the content-based image retrieval, I mean the CBIR. Then I will explain the Mpeg-7 visual descriptors. Then we will see the color layout descriptor, CLD. And then we will see the various steps to compute this CLD. After that, I will explain the Matlab code for implementing this CLD. Then we'll see that how we can apply the CLD on the two images, and we will see their closeness on the basis of color. And then in the last, I will show the effectiveness of the CLD in the process of image retrieval. So now let us go ahead. But before going ahead, I request you to watch following my previous video, which is based on discrete cosine transform DCT of images and image compression. I am recommending this video because the DCT is being used in the computation of CLD. So it will give you the better idea in the understanding of the current video. This video you can get from. Now let us see the content-based image retrieval, CBIR. The CBIR is also known as the QBIC, which is a query by image content. It refers to a process of retrieving expected images from the large image databases according to the contents of the image. The content actually here mean by the color, texture and the shape features of the query image, which can be automatically extracted from the images using various feature extraction techniques. The CBIR is different than the traditional search, which is based on the metadata such as the keywords, tags or the descriptions associated with these images. The keywords actually limit the scope of the query because of the set predetermined criteria. But in the case of the CBIR, it gives us the flexibility to search, which is focusing on the contents of the image because it has no predefined criteria. And here in this figure, you can see the overall procedure of the content-based image retrieval. Actually, we have the image database, which includes the millions of images. With help of some feature extraction algorithm, we extract the features of each image. And then we store these features into the features database. And if we give some query image, we extract the same feature with the help of same feature extraction algorithm. Then we compare these extracted features with the previously stored features in the feature database, and we do actually a similarity check. So this is done by finding some distance such as L1 distance or L2 distance between the feature of the query image and the features which are previously stored in the image database. So once we get the most similar matches, on the basis of that we get the output images, which you can say the most matching images to the query images. So that is the overall procedure of the content-based image retrieval. Now let us see the Mpeg-7 visual descriptors. Actually, the Mpeg-7 is a standard of describing the features of the multimedia content. It provides the world's richest set of audiovisual descriptions. With help of these descriptors, user can search, browse and retrieve that content more efficiently and more effectively than they could using mainly the text-based search engines. The Mpeg-7 is an ISO IEC approved standard, so that developed by the Mpeg, which is the Moving Picture Coding Experts Group. Formerly, Mpeg-7 was known as the Multimedia Content Description Interface. There are actually the many descriptors which are the member of this Mpeg-7 family. So these descriptors can be categorized into the different categories such as the color descriptors. This category includes the dominant color descriptor, scalable color descriptor, color layout descriptor CLD, which I am covering in this current video. Then we have the color structure, color temperature, GOP color, and then illumination invariant color. And the second category we have the texture descriptors. It includes the homogeneous texture, texture browsing, and edge histogram descriptor, which is another very popular texture descriptor. And the next category is the shape descriptor, which includes the region shape, contour shape, shape 3D, and the perceptual 3D shape. And the next category is the motion descriptors, which includes the camera motion, motion trajectory, parametric motion, and then motion activity. We have few more such as the localization descriptor, face identity descriptor, image signature, and the video signature. Now let us see the color layout descriptor, CLD. The color, of course, is most expressive of all the visual features and has been extensively studied in the image retrieval research. The color layout descriptor, CLD, is designed to capture the spatial distribution of dominant colors in an image. For CLD computation, colors are actually expressed in CBIR colored space. CLD is actually a very compact descriptor, therefore it is very suitable for fast browsing and search applications. It is also a resolution invariant. It means if you have the same image of different sizes, you will get almost the similar CLD feature vector. So now let us see various computation steps for computing this color layout descriptor. So the first step is the image partitioning. So in the image partitioning, the input image is divided into the 64 blocks in the 8 by 8 grid. So this makes CLD actually the scale invariant. So here you can see you have one image, and here you can see that how this image is divided into the 64 blocks. And the next step is finding the representative color for each block. So one representative color is computed for each block. So to select the representative color, there are different methods that can be applied, but the very common is the average color of the block that is usually used. Also, after this, the image is reduced to 64 by 64 size, so that each block size reduces to 8 by 8 size. This is not grid size, it is the pixel by pixel of each block. So this is, you can see how. So this is your first step, where image is divided into the 64 blocks of 8 by 8 grid, not size. After that, we get the color average of each block and we get this type of image. Okay, so this is in this image we have the average color of each block. How this average color is computed? Actually, this is not average of RGB value. Actually, this is average of all R values of this block, and average of all G values of this block, and average of all blue value of this block, and combined together we are getting a one solid color in each block. Okay, so now this image is reduced to size 64 by 64 pixels. So now each block will be of size 8 by 8 pixels. Okay, so now let us go to the third step. In the third step, we will change the color space of the image. So right now this average image is in RGB space. So we convert this into the CBIR color space. So this is how we can see. So this is RGB image, and it has a 3 component, I mean the Y, CB, and the CR like this. Okay, and now let us see the fourth step. In the fourth step, we'll go for the DCT transformation. That's why I was recommending to watch my previous video on DCT. Now each color channel Y, CB, and CR. So now we have the 3 matrices Y, CB, and CR. So they all will be transformed into the DCT coefficients by performing the 8 by 8 DCT of each 8 by 8 block. As I said, that now size of the each block is 8 by 8 pixels. So we will go for 8 by 8 DCT of each block. So therefore each block will carry the 64 DCT coefficients. So here you can see, so we have all the 3 channels like Y, CB, and CR, and then we will go for their corresponding DCT. So this is the DCTY, this is DCT-CB, and this is the DCT of CR matrix. And here you can see, if I can zoom it, then here you can see that this one is a 8 by 8 block. This is one 8 by 8 block. This is one 8 by 8 block, and in this one 8 by 8 block you can see that all small blocks, I mean, which is representing one DCT value corresponding to each pixel, they are of dark color. It means it is of very small values, while there is a one square which is of the bright color, and this bright color means it is representing some higher values. Of course, as we know from the DCT, this top left value of DCT is actually representing the DC coefficient of this DCT. So here you can see that in all DCT blocks, this top left component is of the highest value, and that is representing the DC value of each block. Okay. Now let us go to the next slide. In the next step, we'll go for the quantization. So a few low frequency coefficients are selected using the zigzag scanning and quantize to form the descriptor. So for YDCT, only the 6 coefficients are selected, and from both CB and CR we select only the 3 coefficients, and they are quantized to form the CLD. So here you can see that this is your 8 by 8 block, and as I shown you in the previous slide, that all are of dark color. It means they are of very small value, while this this one is representing your DC content of this 8 by 8 image block. And how to select actually these coefficients? I mean, suppose this is your Y DCT, this is the DCT of Y, and then how to select the 6 coefficients from this block. So actually we will select this one first, then we will go for this second like this, and then we will go for this third, and then we will go for this fourth, and then we will go for this fifth, and then 6 like this. So this is the zigzag selection of these coefficients for the Y. Similarly, we will select only the 3 coefficients from CB. So we will select only this 1, 2 and 3. That's it. All these corner coefficients 1, 2, 3. Similarly, we will select 3 coefficients for CR. So for each 8 by 8 block, how many coefficients we have selected? We have selected 6 plus 3 plus 3, I mean the 12 coefficients. And since there are total 64 blocks in an image, so obviously there will be the 7, 6, 8 coefficients to represent one CLD feature of an image. Okay. Now let us go to the easy implementation of the CLD. Of course, this 7, 6, 8 is quite large. And since we have used the average color representation for the each image, it means the each small 8 by 8 square is carrying the same color. Same color. So same color means it is a constant function, because each value is equal for all 64 values. So this is a constant function. So if you take the DCT of it, obviously you will get the all values will be 0 except this the top corner value, which is the DC content of the that image block. The all other elements will be 0. Okay. So as you can see that this one block is having the constant color. So in this DCT, I mean this is square, 8 by 8 square, you can see that only this top corner will be the non-zero and all other will be the 0. And therefore, instead of taking 6, 3 and 3 coefficients from DCTY, DCT-CB, DCT-CR, we'll take only the single coefficient, that is the DC coefficients of each block. So we'll take only these DC coefficients from each block instead of taking 633. So in this case, the number of DCT coefficients for Y is 1, number of DCT coefficients of CB is 1, and for CR it is 1. So per block we have chosen only the 3 coefficients, and for total 64 blocks we will have only the 192 coefficients. So that is the size of your CLD when you choose the average color for each block. So this is the easy implementation, and also it is not of very large size. And now let's see how these coefficients are actually arranged in this 192 length CLD. So these coefficients are arranged like this. So all Y coefficients are arranged first, that means Y DCT1, Y DCT2 to Y DCT64. Then we arrange all CB coefficients, and then we arrange all 64 CR coefficients from each block. So this is my CLD vector, which is finally computed for this image, and it has a length 192. After that, we will go for the Matlab implementation for this CLD. So this is the Matlab program. Here what I'm doing, actually I'm reading 2 images, and then I'm finding the CLD of these 2 images, and then I'm comparing the CLD of these 2 images by finding some distances, such as L1 distance, L2 distance, and one weighted distance that is proposed by the Mpeg-7. And then I will show you that how these distances increase in case you take the 2 dissimilar images in terms of the colors. So here you can see that by executing these commands, you will first choose your first image by IMRead, that will go into the IMG1, and with these lines you will read your second image, color image, and by IMRead it will go to the variable IMG2. And here I am finding the CLD of these 2 images. So CLD1, that is the CLD of the first image, and then CLD of the second image. So here I have used this custom function, which is the find CLD. This is not Matlab function, this is my function which I have written. So in the coming slides I will explain what is inside this find CLD function. And here I am plotting these CLD, these CLDs, I mean plotting CLD1 and then plotting CLD2. So by this way graphically I can see the differences between the CLD1 and the CLD2. And here I am separating the Y part and CB part and CR part for these 2 CLDs, I mean CLD1 and CLD2. These parts actually will be used in computing the distances. So let us see how. Actually this is one way to compute the distance between the CLD1 and CLD2. This is known as the weighted distance. It is proposed actually by the Mpeg-7. Okay, and here Mpeg-7 suggests some weights such as 2 to 4 for Y, CB and CR part of the CLD. So it is giving the maximum weightage to the CR, that means the chroma samples which are defining the colors actually. So this is how we can compute this distance. So this distance dw equal to the square root of some CLD Y1 minus CLD Y2. That means the Y part is compared with the Y part with a weight 2, and then CB part is compared with the CB part with a weight 2 as we have suggested, and then CR part is compared with the CR part with a weight 4. So this is how we can compute this weighted distance, and it is displayed by this disp command. And this is how we can compute the L2 distance between CLD1 and CLD2. That is simple, which is the square root sigma CLD1 minus CLD2 whole square. The same thing you can achieve by this Matlab command also. You can use this command also in place of this, that is the norm CLD1 minus CLD2 comma 2. So that will calculate the L2 norm, that is your L2 distance, and then displaying this L2 distance, and here we are computing the L1 distance between CLD1 and CLD2. So that is simply the sum, the sigma absolute CLD1 minus CLD2, and this you can similarly you can achieve with this Matlab command, that is finding L1 norm. So norm CLD1 minus CLD2 1. So this is the another way, and then displaying this distance. Okay, so this is how you can compute the CLDs of two images, and then you can compare those CLDs on the basis of these distances. And as I said in the previous slide, that we have used this function find CLD, which I have coded to compute the CLD. So let us go inside this function. So this is my function find CLD to get CLD vector. So let us see what I am doing inside it. So this is the definition of your function. I am just passing the input RGB image. So first we are calculating the size of this image. I mean the rows and columns, and then we are doing some operations to make it divisible by 8. Actually your image is not always possible that your input image is divisible by 8 in terms of the integers output. Okay, so if your image has some size which is not divisible by 8, then we are resizing it to the nearest dimension so that it can be made divisible by the 8, so we can get the integer output. Okay, now we are defining a block of size R and C, and then we are defining a mask. So this mask is actually used to isolate that the DC component of that 8 by 8 block. So as I shown you in the previous slide, that all these coefficients are 0 except this DC component of this 8 by 8 block. So this mask will be used to isolate this DC component. So you can see that this is 1 and rest are 0. So we will directly multiply this mask to the matrix to isolate this DC component. And here we are using actually the block processing. So first we are defining averaging operation. So what was the first step? The first step was to get the average image. Image which has the average color in each block. So this is how we are defining this average operation. That means we are doing a block processing of the input image which has the block size R and C. Okay, and this is your block averaging operation. So averaging operation is simply that we have defined that matrix of size R and C which has only the 1 1 1 1, all values are 1. Okay, and it is multiplied with the mean of the block size. So mean of block size, obviously it is the average of each block. Okay, and in this line we are first resizing the image, as I said, to the 64 by 64 so that your each block becomes of size 8 by 8. And now we are changing its color space from RGB to YCBCR. So this variable YCBCR is carrying all the 3 planes, Y, CB and CR. Then here again with the block processing we are finding the DCT of each block. So this is defining the DCT operation for each block. So I have used the DCT2 function, which is a Matlab inbuilt function to compute the DCT of a matrix. So your block will go to this DCT2 functions, and which is multiplied this mask. As I said, I will multiply this with a mask, so it will isolate my DC component, and all other coefficients will be 0 except that DC coefficient. And here I am applying this block processing on the Y block. So here I am extracting only the Y plane from the YCBCR, and the chosen size of block processing is 8 by 8, of course, and this is the operation, this one which I have defined. So this will compute the DCT of each block, and then it will multiply with the mask. So in the Y DCT you will have all 64 blocks, and they have only the top left corner component non-zero, which is actually your DC component, and all other coefficients will be 0. Similarly, the DCT of CB is computed, and then DCT of CR is computed. And then we are collecting all these DC coefficients with this find function. And then once they are collected, then we are combining all these collected Y coefficients, collected CB coefficients, and collected CR DC coefficients like this. So we are placing them side by side to make this feature vector. But this is not a one line CLD feature vector. Actually, it is of 64 by 3 size. Why 64 by 3 size? Because for all 64 blocks, the total number of computations will be 64, and each block has 3 values. I mean, the first value of YFV, second value of CBFV, and third value of CRFV. So it has a size 64 by 3. So now I am reshaping it to achieve a one row vector. So here the CLD is a single row vector which is of size 192. So this is how we can compute the CLD of the image. And now let us go to the Matlab where I can show you how we can run this program and what type of output we will achieve. So this is my program which is already written there, and this is the corresponding function find CLD. You can see that mask is defined here, and all block processing commands are expressed here. So I will run this program mycld.m. So let me press this run button, and it asks me to choose my first image, select color RGB image 1. So I'm choosing let's say this baboon. Okay, open, and it is asking me to choose the second image. Just for demonstration purpose, I am choosing this image again as the second image. So I am choosing the same image as image 1 and image 2. So what will be the CLD? Obviously the CLD will be same and the distances will be the 0. So let me see whether I get it or not. So okay, so this is the CLDs are plotted here. You can see the CLD1 is in blue color, CLD2 is in red color, and here you are not able to see the blue color. It means both the CLDs are exactly equal in the magnitude. Okay, that's why they are overlapping each other. That's why you are not able to see this blue color. So obviously, as I said, since I have chosen both the images same image, that's why we are getting the overlapping. It means we are getting the same CLD for both the images. So here you can see that all the distances calculated are 0. I mean the weighted distance is 0, L2 distance is 0, L1 distance is also 0. So that is natural. Now let us select a few different images. So first I am selecting this tomato image, okay, and then second as a second image I am selecting again a tomato image, but this image is slightly different, this first image, and let's see how. So this is your first image, you can see tomato, and this is the second image. So this is actually corrupted by a few lines, you can see with these few black lines. So this will help you to understand actually the color layout descriptor. I mean the color layout descriptor help us to get the distribution of the color inside the image. So let us see how this these black lines will distort it. So let me choose the second image and let's see what type of output I get. Okay, so this is here you can see both the CLDs simultaneously, blue and red. So blue one is of first image, red one is of the second image. So you can see that both the CLDs are quite similar, except there are few differences at certain places because of those black lines. Okay, Now let us see the distances, and here weighted distance is 419, L2 distance is 151, and L1 distance is 1504. So these two images are obviously quite similar with each other except those black lines. But in case of retrieval, obviously if you select the first tomato image, obviously the second image should come as a result. Those black lines should not affect the results, because as the overall color distribution, both the images are almost the same. So it is validating this fact. Now let me find a few more images, and this time I will choose entirely different images. For example, now I am choosing this flower as a first image, and then this Lena as second image. Okay, now you can compare both the CLDs. There is a quite difference, because obviously the color layout is different of these two images. So now let us see the distances. Now distances of course will be the huge. So weighted distance is 10635, L2 distance is 4336, and L1 distance is 45928. So obviously you can see that distance has increased a lot. And now let me show you the scale invariance. The scale invariance means actually as a first image I will select one image, and as a second image I will select the same image but of the reduced size or enlarged size. So here I am choosing this Lena as first image, which is of size 512 by 512. And as a second image I am choosing the same image Lena, but its size is only the 64 by 64. There's a huge difference in the size. I can show you here. So this is your 64 by 64 image, very small, and this is 512 by 512. So as CLD claims that it is a scale invariance, so let me see whether I will achieve the similar CLDs for both the images or not. So this is my second image. So now you can see the CLDs for these two. So obviously for these two images, which by the content are same but they are different in the sizes, here you can see that both the CLDs are very much similar to each other, except very small differences at few places you can see. So this shows the scale invariance of this CLD, and you can see the distance also. This is also very small. I mean the 88, 32, 128, like this. So this shows the scale invariance property of the CLD. So obviously the CLD will have the significant output or it has a good strength in the image retrieval. So I can show the effectiveness of this CLD in case of image retrieval. So for this purpose I have actually already written a program of image retrieval, which is based on this color layout descriptor. In this video I'm not explaining this code, I'm not giving this code to you, because if I will add this, the length of the video will be too much. So this image retrieval implementation I will explain in some coming videos. Here just I am showing its execution, so that you can have an idea of the effectiveness of the CLD. So for this purpose I have used one flower database. So this is a flower database which has total 210 images. So all the images are first converted into their feature vectors, I mean the CLDs, and then I will choose any one image out of these 210 as a query image, and then we will retrieve the most similar images of the flowers, and we will see the effectiveness of this CLD, whether we are getting the relevant images or not. So let me run this program. So let me execute it, and it asked me to choose the query image. So let me select the query image, this one, image number 21, and let me see how I get the different matching images. Okay, so this is the output you can see. So your this first one is your query image, and here I have retrieved the first 5 nearest matches. So this is your first match, this is second match, third, fourth and fifth. So you can see that you are getting the similar images for this query image out of the database. So it is the effectiveness of your CLD. Now let me judge for more few inputs. So now let me select this image, a white color flower, and this is the output. Again, you can see that I am able to retrieve all the similar images from the database. So this is a query image, and these all 5 are your retrieved images which are similar to your query images. So let me run again for a few more. Let me select this rows and let's see what type of output I will get. Okay, again I'm getting very impressive results. So this is a query image, and this is your first, second, third, fourth and fifth images. So now let me try a complex type of input. So I will select a difficult image. Let's say this is 100, which is a purple color. So I'm choosing this image number 100, and let's see what type of output. Okay, so this is the output. Again, CLD gets full marks in this case. So this is a query image, and these are all retrieved image from the database. So you can see that how the CLD is effective in the process of image retrieval. So you can use in the implementation of the image retrieval. If you are making some project on it, I strongly advise you to use CLD for your case. Okay, that's it for this video. I hope you have enjoyed a lot and you have learned few new things from this video. So I really thank you all for watching this video and devoting your precious time. I request you to please like it, share it, and stay tuned for more such interesting videos to come. Till then, goodbye.